And then we will have the linear CEF expression. So we use the matrix to represent this whole things. So I need to point out that here we use linear, and from the previous slides we do not have linear, which means actually the function can be non-linear functions. And only starts from here, I emphasize it must have to be a linear one. Okay, so let's start. And let x be the k/1 vector, which is looks like this one. And here 1 means the constant. And the CEF is just mx equals the linear combination of x and beta. So here is the x transpose beta. So there are the similar things, but we didn't use the transpose in this textbook. And where beta is another k/1 coefficient vector. And we can write this like mx is which means this x1, x2, xk minus 1, and 1, and then beta. Yeah, looks like this one. And this is a linear CEF model. It's also often called the linear regression model or the regression of y on x. And I believe that during your first course of econometrics, or the second, but at least the first chapter, you will learn the linear CEF. And it may be also called OLS when you adding some assumptions and conditions to the linear regression model. And let's go to the next part, which is the linear projection coefficient, or the linear projection model. So for this one, it is a little bit different from the previous one, which means the previous theorem showed that the conditional mean mx is the best estimator in the sense that it has the lowest mean squared error among all predictors. But it could be nonlinear or linear. And by this extension, we can define an approximation to the CEF by the linear function with the lowest mean squared error among all linear predictors, which means this one is the best linear predictor. And it's based on 3 assumptions. The first one is the expectation of y squared is finite, and the expectation of x norm square is also finite. And then the expectation of x transpose is positive definite. It's kind of similar to the third property of the inner product space. And we define the best linear predictor of y given x is like the x transpose beta, where beta minimizes the mean square prediction error. It can be represented like this one. And it will look a little bit similar to the previous one, which we only use x transpose beta to replace the previous notation. And the minimizer looks like this one. So which means we use the first order condition to get the coefficient beta, and it called it the linear projection coefficient. and it have some properties. So under the assumption, the moments EXX transpose and EXY exist with finite elements, so which just based on the assumption here. And the second, the linear projection coefficient exists and is unique and equals this one. So I want to prove the same. Let's first write down the S beta here, which is this one. And then we take the partial derivative of it based on beta, and which is just the first order conditional. I will eventually take the partial derivative. First, let us expand it to some parts. The first one is y squared, and the second one is beta transpose E xy. So we use this one because they are all matrices. And then we take the partial derivative of it. So you notice like this one is not include beta, so just cancel it. And then this one, we cancel this one and write down the other parts. And for this one, let's cancel the first one and write down the other things. Notice that it's actually a beta square here. So we need to write down 2 and x transpose beta. Then it have to be 0 to minimize this. Then we can rewrite it by moving beta to one side and the other things to other side, we will have transpose. You will find that it's a little bit similar to what we have learned from the last class of the linear algebra course, but it has a notation of expectation here. And if we use qxx to represent this thing and qxy to represent the other thing, then it will look like better, but actually it's the same things. And here qxy is a k by 1 matrix, and exx is a k by k matrix. And then we know that beta is actually also a k by 1 matrix. And we done the proof. It's just the same things. And then the third property, the best linear predictor of y given x is this one. So actually we just use here beta to substitute it here. So I don't think it need a proof. And then the projection arrow E equals y minus x transpose beta exists, and it satisfies this condition and emphasize this condition. So let's give a proof for this one. Let's first substitute E here to y minus x transpose beta. And then let's separate it to some parts, which is X transpose and beta here. Now we want to substitute beta to what we have found before, which is X transpose inverse and EXY. So notice that here, because it's itself and itself inverse, then it's just 1. So we ignore it. So it's EXY minus EXY. And turns out to be 0 at the end. Then we prove this one. And for the fifth property, if f contains some constants, then the expectation of the arrow is just 0. So you can see if it is a constant like a, e here, and we can write it's like, we can factor out a, and then because this is 0, so the whole thing is 0. So we have done the proof of it. And also the last property, if ey to the power of r is finite, and e the norm of x to the power of r is also finite, then for r is greater or equals to 2, then the arrow term to the power of r is also finite. So I don't want to prove this one because it's not so correlated with the course. And if you are interested what I have shown, you can check of this book, which I believe is which is the textbook for the PhD course, economics. So you can check of this book, and this is actually the second chapter of this book. And I hope you can get the general idea of what curve fitting is, and what the conditional expectation function is, and what the linear CEF and also the linear projection model is, and why they are best predictors in some sense, and what properties they have. And thank you for watching the video. Have a nice winter break. Thanks.